Here we'll talk about the Aldol reaction. So this is a reaction where we'll produce an enolate ion, and then that enolate ion will continue in the reaction. So the Aldol reaction, you could start with an aldehyde or a ketone. And you could add acid or base. We're going to focus on the base catalyzed reaction. And so an example would be sodium hydroxide. And if you add this in water, you have both OH minus and H2O present. The product of this reaction contains an alcohol group. We still have one carbonyl. And we have a new carbon-to-carbon bond. So let's do some highlighting. So this part of the molecule has an aldehyde functional group. Looks very similar to the starting material, but we have this new carbon-to-carbon bond there from the alpha carbon to the original aldehyde. So new carbon-to-carbon bond, and then we also have an alcohol group. And so this is called an Aldol reaction because we have both an aldehyde and an alcohol. So we form an aldol product. So let's kind of list what's going on here. We have a new carbon-to-carbon bond that is highlighted in the molecule in this blue color. We have an alcohol group, and this alcohol is on the beta carbon. So relative to the carbonyl, adjacent carbon is the alpha carbon, one carbon over is the beta. So we have an alcohol on the beta carbon. Sometimes these are called beta hydroxy groups. Remember, hydroxy is another word for alcohol. These are acid or base catalyzed. And also possible with ketones. Now again, we'll focus on the base catalyzed mechanism. And yes, they are possible with ketones. The aldol name comes from using an aldehyde as the starting material, but we would still call it an aldol reaction if you're using a ketone. So these reactions occur naturally in biological pathways. So our aldol reaction in the Krebs cycle and in gluconeogenesis. So there are two examples of where the aldol reaction occurs in biological pathways. It's also widely used in industry. We talked about this with organometallic reagents. That's very useful for someone producing molecules to be able to create a new carbon-to-carbon bond without having to use a metal catalyst. So in this reaction, as opposed to when we're working with organometallics, there's no metal in the reaction here. So this is, again, a very useful mechanism. So let's go through the mechanism, again, in basic solution. So look back at the reaction scheme. We start with an aldehyde. We could have different carbon chains here so that our group can be different. We will start with that acetaldehyde here. So we'll just have a CH3 group as the R group. So we've got a CH3. We have 3 hydrogens here bonded to that carbon. We are in basic solution. We have sodium hydroxide and water. So the first step, we look at our aldehyde exposed to basic solution with OH minus from sodium hydroxide. We will remove an alpha hydrogen. So the first step is a hydrogen or a proton transfer. And this is just forming the enolate ion. This happens in equilibrium. And again, we can show the enolate ion with a negative charge on the carbon. So we removed one of those hydrogens, that becomes a lone pair. We have a negative charge on this carbon. As we've done in the past, we can also show resonance here, where we now have a double bond between the 2 carbons instead of a negative charge on the carbon. And the negative charge is now on the oxygen. So we have resonance here. This structure with the negative charge on oxygen is the more stable resonance structure. Because the negative charge is owned by the more electronegative atom, oxygen, as opposed to carbon. But for the Aldol reaction, for the mechanism, we use and we show the resonance structure with the carbon owning the negative charge. So we use and show the structure with a negative charge on the carbon. Now, looking back to that structure where we have a negative charge on the carbon, this carbon has electron density. It has a pair of electrons that it could share. So that makes this carbon a nucleophilic carbon. So the C minus, carbon with the negative charge, is now nucleophilic. Okay, so with the base, we generate the nucleophilic carbon for some of the aldehyde starting materials. Now, if we have abundant aldehydes and we have the enolate, again, we're doing the mechanism, so showing negative charge on that carbon. I'm not showing the hydrogens here just to keep it simple. We just said in the last structure, this is a nucleophilic carbon. And we know from our previous reactions with aldehydes, ketones, carboxylic acids, etc., this carbon, that's the carbonyl carbon, is an electrophilic carbon. So after we do the proton transfer in this first step here, this is a proton transfer, we generate the enolate ion that generates a nucleophilic carbon that is near an electrophilic carbon for another aldehyde that has not gone through that proton transfer reaction. Well, now this nucleophilic carbon can create a bond to the carbonyl carbon. And then we break the pi bond. So this next step is nucleophilic addition. So this step forms a new molecule where we have combined the enolate formed in the first step and the aldehyde as one of the starting materials. So the new structure here, we've got carbon to carbon bond, carbon to oxygen, single bond. We broke that pi bond. Now this carbonyl carbon, I'll use green because we use that for the curved arrow, is now bonded to the carbon from the enolate. And then the rest of that molecule, or that part of the molecule, remains the same. Now we still have a hydrogen bonded to that carbon where we just added the new bond. So that's still present, and we have this new carbon to carbon bond here. So we've got a negative charge on the oxygen. We can neutralize that oxygen by giving it a proton. We have both water and OH minus present in solution. So using the water, that can give a proton to that negatively charged oxygen. So this last step is also a proton transfer. And we have generated a molecule with an aldehyde and an alcohol on the beta carbon. So this is the Aldol product.